Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Beyond the Big Bang, how the mirror hypothesis could redefine our universe. We find ourselves in an unprecedented era for expanding our knowledge about the universe. With the help of advanced technology and scientific innovations, we are able to peer deeper into the cosmos than ever before. Our most powerful telescopes have revealed a surprising simplicity in the structure of the universe when viewed on its largest observable scales. Meanwhile, on the opposite end of the spectrum, the Large Hadron Collider, LHC, has given us a detailed look at the smallest building blocks of the universe, with results that fall neatly within the framework of known physics. Contrary to expectations, these findings reveal a universe that is much more orderly and predictable than many theorists once imagined. For decades, scientists have been developing theories to explain the fundamental structure and behavior of the cosmos. Among these theories, two have emerged as the dominant paradigms: string theory and cosmic inflation. String theory, a highly mathematical framework, posits that the universe's most basic building blocks are not particles but tiny, vibrating loops or strings. In order for this theory to function, however, it assumes the existence of additional spatial dimensions beyond the three that we can perceive. These extra dimensions are thought to be minuscule and curled up, making them effectively invisible to us. However, the multitude of ways in which these small dimensions could theoretically curl up produces an almost infinite number of possible configurations, each of which would generate a different set of physical laws in the dimensions we can observe. This complexity makes string theory difficult to test and verify, as each possible configuration could lead to a unique set of fundamental forces and particles. On the other hand, cosmic inflation is a concept proposed in the 1980s to explain certain large-scale properties of the universe, particularly its smoothness and flatness. According to this theory, in the moments following the Big Bang, the universe underwent a brief but extreme phase of rapid expansion. This burst of inflationary growth would have smoothed out any irregularities and resulted in a relatively uniform and flat universe, which aligns with what we observe on cosmic scales today. Inflation also provides a mechanism for understanding slight variations in energy density in the early universe, which eventually allowed certain regions to collapse under their own gravity, forming the galaxies and cosmic structures we see today. Over the past few decades, astrophysicists have mapped these density variations with increasing accuracy by studying the cosmic microwave background radiation, the afterglow of the Big Bang, as well as the three-dimensional distribution of galaxies. Despite its appeal and utility in explaining certain features of the universe, inflation has faced challenges when subjected to experimental verification. One of the main predictions of most inflationary models is that the rapid expansion of space should have generated long-wavelength gravitational waves, ripples in the fabric of space-time. Detecting these waves would serve as a smoking gun confirmation of inflation. However, despite advances in observational technology, no such signal has been detected. In fact, as experiments have grown more precise, more inflationary models have been ruled out, and the evidence for inflation as a whole remains inconclusive. This growing discrepancy between theoretical expectations and observational evidence has led some scientists to question whether inflation is the best explanation for the universe's early history. Another intriguing aspect of inflation is the concept of the multiverse. During inflation, different regions of space could experience different rates and amounts of expansion. This variation could theoretically result in a multitude of bubble universes, each with unique physical properties. In this scenario, our observable universe would be just one small part of a much larger and more diverse multiverse, where each bubble could operate under a distinct set of laws and constants. Although the idea of a multiverse has gained traction in some circles, it remains purely speculative. So far, no observational evidence supports the existence of other universes or the extreme variety of physical laws that they might contain. One possible explanation for the gap between theory and observation is that we are simply limited by the scales we can currently probe. Perhaps the expected complexity does indeed exist but lies hidden at scales beyond our reach, either far smaller or far larger than those accessible with current technology. Alternatively, it is possible that the universe is genuinely simple and orderly at both extremes, and that this simplicity is a fundamental characteristic of its nature. If this latter possibility holds true, we may be closer to unraveling the universe's most profound mysteries than we previously thought, and some of the answers might already be within reach. Given the mounting challenges to string theory and inflation, some scientists have begun to explore alternative models. In recent years, new approaches have emerged that attempt to explain the structure and behavior of the universe without relying on these traditional frameworks. These alternative models draw inspiration from the observed simplicity of the cosmos and aim to develop testable theories grounded in empirical evidence, rather than the intricate mathematical assumptions that underpin string theory and inflation. One of the biggest mysteries in cosmology is the nature of the Big Bang itself. According to Einstein's theory of general relativity, if we trace the expansion of the universe backward in time, space eventually contracts to a single point known as the initial singularity. At this singularity, the density and temperature of the universe would have been infinitely large, posing a significant challenge for our current understanding of physics. In attempting to make sense of this singularity, researchers noticed a curious symmetry in the laws that govern massless particles and light. This symmetry, known as conformal symmetry, suggests that neither light nor massless particles would actually experience the collapse of space at the Big Bang. Building on this insight, some researchers have proposed a novel way to view the Big Bang, not as a beginning in the traditional sense, but as a mirror boundary in time. In this model, time moves forward on one side of the mirror and backward on the other. This mirror hypothesis has profound implications for our understanding of the universe. For example, it offers a potential solution to one of the most basic puzzles in physics: why there is an apparent asymmetry between matter and antimatter. In the current universe, matter particles outnumber their antimatter counterparts, leading to a net abundance of matter. According to the mirror hypothesis, the Big Bang could have produced a mirror universe on the other side, where time flows in the opposite direction and antimatter particles dominate over matter. This mirror universe would restore a fundamental symmetry known as CPT symmetry, which states that physical processes should remain unchanged when time, space, and particle types are inverted. In this way, the mirror hypothesis provides a novel explanation for the observed matter-antimatter asymmetry without requiring additional assumptions. Another intriguing application of the mirror hypothesis relates to dark matter, the mysterious substance that makes up a significant portion of the universe's total mass. Researchers have long suspected that heavy, right-handed neutrinos, hypothetical particles that do not interact with other matter except through gravity, might account for dark matter. The mirror hypothesis allowed researchers to calculate the expected abundance of these right-handed neutrinos in the early universe, leading to a prediction that could potentially explain dark matter's elusive nature. One testable outcome of this theory is that if right-handed neutrinos constitute dark matter, one of the three known types of light neutrinos should be massless, a prediction that current and future observations can test by studying the large-scale distribution of galaxies. Yet another major puzzle in cosmology is why the universe is so uniform and spatially flat on its largest observable scales. Originally, inflation was proposed as a solution to this problem, as the rapid expansion in the early universe would have smoothed out any irregularities. However, recent advances in statistical physics and thermodynamics have provided an alternative explanation. Entropy, a concept that measures the number of possible configurations of a physical system, can be extended to cosmology to calculate the entropy of entire universes. When this approach is applied, it suggests that the most likely universe would be one that is flat and expands at an accelerated rate, just like the universe we observe. This statistical explanation provides a natural alternative to inflation, without the need for the complex assumptions required by the inflationary model. The mirror hypothesis also offers insights into the origin of cosmic density variations, which are typically attributed to inflation. According to the mirror model, a particular quantum field with no intrinsic dimension could produce the observed density fluctuations without inflation. Importantly, these density variations would lack the gravitational waves predicted by inflationary models, a prediction that aligns with current observations. While these results are promising, further theoretical work and experimental verification are needed to establish the mirror hypothesis as a viable alternative to the inflationary paradigm. Regardless of whether the mirror hypothesis ultimately proves correct, its development highlights an important shift in the field of cosmology. By taking the observed simplicity of the universe as a guiding principle, researchers have shown that it is possible to construct elegant and testable theories without relying on the complexity and unpredictability of the traditional orthodoxy. This approach challenges scientists to rethink long-held assumptions and to explore new paths that could lead to a deeper understanding of the cosmos. As we continue to push the boundaries of our knowledge, it is essential to remain open to alternative explanations and to question whether established theories truly capture the essence of the universe. By combining empirical observations with innovative theoretical models, we may one day achieve a comprehensive understanding of the cosmos, one that is grounded in simplicity and consistency rather than complexity and conjecture. Through this ongoing pursuit of knowledge, we stand to gain insights not only into the nature of the universe but also into the fundamental principles that govern all of existence.